So what we want to do in this section is introduce the equation for a wave. And so let's start by stepping back and looking at the equation for simple harmonic motion, because these two equations are very similar. Now part of that is because as our wave moves, the particles that make up the wave are oscillating up and down through simple harmonic motion. So it's not by accident that these equations are going to look as familiar as they do. So our equation for simple harmonic motion said that if you're interested in the displacement from equilibrium, which we've called x here, and that was a function of time. So if you wanted to know what was the displacement from equilibrium at some time t, that was going to be equal to, well, a here is your amplitude. That's another way of saying what's the maximum displacement, maximum value of x, times we've got a sinusoidal function, and in this case we've picked it to be cosine. What we're plugging into the cosine is known as the phase, and it had two pieces. One was omega t, so the angular frequency times time. The second was the phase shift. If the phase shift is 0, then at t equals 0, since this is a cosine curve, you should be at your maximum displacement from equilibrium. If at t equals 0, you're not at amplitude, then you've shifted the curve some amount, and the phase shift is going to tell you what that amount is. So here's our equation for a wave, and again notice it's very similar in structure. And so the first thing we'll point out is it's still using a sinusoidal function. It's just that we picked cosine in talking about simple harmonic motion, and here we're going to choose to use sine. If we look at each of these pieces, so let's go through these pieces one at a time. So again, we start by thinking about the displacement. So why here is the displacement? It's just that now it doesn't only depend on time. It still does depend on time, but it also depends on position. So as your wave travels, where you're located also matters in terms of how large the displacement is from equilibrium. Second piece is the amplitude. And again, the amplitude is just another way of saying what's the maximum displacement. So the amplitude here is just like saying what's the maximum value of y. All these pieces we're going to plug in to the phase. And so the first one here is k. And k is known as the angular wave number. It's related to the wavelength. So lambda, this Greek letter lambda, is what we use to represent the wavelength when we're talking about waves in physics. And the angular wave number k is 2 pi over lambda. The 2 pi has units of radian, because again it's the amount of radians around a circle. Lambda as the wavelength has units of meters, so k, the angular wave number, has units of radians per meter. We're going to take k and we're going to multiply it by x. And so of course x has units of meters. So when you multiply k with units of radians per meters times x units of meters, we're going to get something with radians. Here we have three pieces that make up our phase. Each of those individual pieces is going to have units of radians. That's what we're plugging in to our sine function. Next thing we've got is between these first two terms. So there's a kx and then there's an omega t, and there's a plus and minus between those two. And whether this is plus or minus tells you the direction the wave is traveling. So if it's kx plus omega t, then your wave is traveling in the negative x direction. If you have kx minus omega t, well, now your wave is traveling in the positive x direction, which we typically draw out to the right. So using our standard coordinate system where positive x points to the right, then whether you've got a plus or a minus tells you whether your wave is traveling to the right or to the left. The next term has two pieces, and again the first one is the angular frequency. The angular frequency is related to the frequency and related to the period, just like it was in simple harmonic motion. And so the angular frequency, just like we've seen before, has units of radians per second. I'm going to multiply the angular frequency times time to get this second product in my phase. And of course, if omega has units of radians per second, time has units of seconds, then again omega t has units of radians. So just like kx, omega t as a product has units of radians. Next piece is the phase shift. And again, its purpose is the same here as it was in thinking about simple harmonic motion. The phase shift is basically saying, well, when everything else zeroes out, if you plug 0 into a sine function, you should get 0 for your answer. So you should have no disturbance when you plug in kx plus omega t or kx minus omega t equals 0. So if your wave isn't at 0, at t equals 0 and x equals 0, then you've shifted it. And the phase shift is going to tell you how much you've shifted your wave by. All three of these pieces make up the phase. And again, kx, omega t, and phi all had units of radians because when we plugged the phase into our function, we want it in units of radians. So this gives us our wave equation. Part of what we want to make sure we can do is simply just read off the pieces. So we're going to have to both, given an equation, figure out what these values are, or if we're told what these values, we're going to need to build an equation. So we want to make sure that we understand all of these pieces. Now, if I want to see how that equation plots out, well, there are two ways that I can plot it. So again, because y depends on both position and time, I can draw a plot in both position and time. And so if I start by plotting y, the displacement from equilibrium, as a function of x at a single instant in time. So this is basically saying, take a picture. That picture is going to tell you what's going on at some point in time, and then see how your wave spreads out over space. So that's effectively what this is here when we're plotting y as a function of x. And so there are some things that we can read off looking at a graph like this. The first is we can read off the amplitude. So the amplitude again is just, well, what's the distance from the center line of your wave to the peak or the trough. I can also read off the wavelength of the wave here. So again, the wavelength of the wave is just, well, what's the distance from peak to peak or trough to trough. Once I know the wavelength, then I can calculate k. A, I read off. K, I read off the wavelength and then calculate k using the wavelength. I can read off the phase shift. And so at t equals 0, x equals 0, if this is a sine function, my wave should be 0 if my phase shift is 0. If not, I need to figure out what that is. And so this shift here is again something that I can read off, and it's some fraction of the wavelength times 2 pi radians that I've been shifted left to right. So these are the three things that I can read off if I'm looking at a displacement versus position. So y versus x. I can read off the amplitude, I can read off the wavelength, which lets me calculate k, and then I can read off the phase shift. Well, if I make a second plot, I can also plot the displacement as a function of time. So this is basically saying, watch some particular point. So focus in on one particular point in your wave, and then watch what that point, how it oscillates up and down as your wave travels past. And so again, here there are some things that I can read off in terms of values in my equation that I can read from this plot. First again is the amplitude. It's just the maximum height in y. It has to be the same amplitude as what I got when I was looking at my y versus x plot. 2 is, well, I can't read off omega, but what I can read off is the period of the wave. So how long does it take for the wave to start to repeat? So in the same way that I could read the wavelength in my position plot, how far does the wave travel before it starts to repeat? In my time plot, I can read off the period. How long does it take before the wave starts to repeat? And then once I know the period, 2 pi over the period gives me the angular frequency. So again, I can read off t and calculate omega. And then the last thing is, again, I can read off the phase shift. So I can read off what fraction of a period has my wave been shifted by, and then convert that into some fraction of 2 pi radians. So when I'm looking at a position versus time graph of my wave, I can read off the amplitude, I can read off the phase shift, and I can read off the period and use that to calculate omega. Last option, of course, is so let's look at an example. I'm given a displacement versus position, y versus x, and a displacement versus time graph, and what I want to do is figure out what the equation of my wave is. Here's the graph showing me the displacement as a function of position at time t equals 0. Here's a graph showing me the displacement as a function of time at x equals 0. And so I'm going to read off the things I know I can read off of each graph and then use them to put together my equation. So for starters, on my position graph, I know I can get the amplitude. That's 4 meters. What's the height of my wave? It's 4 meters. What's the wavelength? Well, from peak to peak, that's 1 meter. Just reading off, at this point it's at 2 meters. Here it's at 3 meters. So 3 minus 2 is 1 meters for the wavelength. And again, phi, what I see is it's a quarter of the wavelength that's been shifted over. Right? So that's 1/4 of the full wavelength. And so 1/4 times 2 pi is pi over 2. If I look at my displacement versus time, again, I can read off the amplitude. I get the same value. It's still coming up to a height of 4 meters. I can read off the period. So peak to peak in my time plot tells me the period. In that case, that's 2 seconds. It goes from 2 seconds to 4 seconds to repeat. So the period's got to be 2 seconds. And then again, the phase shift, same thing. It's 1/4 of the wavelength. And so 1/4 times 2 pi tells me that the phase shift is going to be pi over 2. I can use my wavelength value to calculate k. K is 2 pi over the wavelength, 2 pi over 1, so that's 2 pi radians per meter. I can use my period value to calculate omega. So the angular frequency is 2 pi over t, so that's 2 pi over 2, which is pi radians per second. So now I have the amplitude, k, omega, phi. I have all 4 of the pieces that I need to plug into my equation. The equation of the wave represented by these 2 graphs is 4 sine, k is 2 pi times x, minus omega is pi times t plus pi over 2. So here's the equation of the wave shown in these 2 plots.